Welcome to AI Daily, your daily briefing on AI, machine learning, and software engineering. I'm Jordan, joined by Alex, and we're bringing you today's top stories and in-depth analysis.
AI moves fast. Here's what matters. This is AI Daily for January 8th, 2026. Despite requiring 100x less power than traditional methods, SpikySpace still manages to predict time series with surprising accuracy. But how can a system that only spikes deliver reliable forecasts? Today, eat real food. SpikySpace, a spiking state space model for energy-efficient, sample-efficient, neurosymbolic deep reinforcement learning. Plus, our deep dive into SpikySpace, a spiking state space model for energy. Let's go!
Here's your AI Daily News Roundup for January 7th, 2026. First up, something a little different, trending on Hacker News, an article from realfood.gov titled simply, Eat Real Food. Now, you might be thinking, what does that have to do with AI? Well, the massive discussion in the comments is fascinating. People are raising concerns about the energy consumption required to train AI models, particularly those used in personalized nutrition recommendations. There's a growing ethical debate about whether we should be prioritizing computationally intensive AI-driven diet plans when, arguably, simpler, lower-tech advice like eat real food might be just as effective and far more sustainable. For software engineers, this highlights the need to constantly question the real-world impact and energy footprint of our algorithms. Are we optimizing for marginal gains while overlooking the bigger picture of resource consumption? This thread is definitely worth a read, even if just for the philosophical food for thought. Moving on to some more technical developments, we have a new paper on Archive titled SpikySpace, a spiking state space model for energy-efficient time series forecasting. Now, this is particularly relevant for those of you working with edge devices and IoT applications. The researchers are proposing a spiking neural network, or SNN, which is a type of neural network that mimics the way biological neurons communicate using brief spikes of activity. The crucial point here is energy efficiency. SNNs are inherently more energy efficient than traditional artificial neural networks because they only perform computations when a spike occurs. This is especially important in scenarios like traffic management or industrial monitoring, where devices need to run continuously on limited power. For AI practitioners, this presents a potential shift away from power-hungry deep learning models and towards more sustainable, hardware-friendly architectures. It's something to keep an eye on as we push AI closer to the edge. In other news, there's a paper making waves in the reinforcement learning community: sample-efficient neurosymbolic deep reinforcement learning. One of the biggest hurdles in RL is the sheer amount of data required to train agents. This paper tackles that problem head-on by integrating symbolic knowledge into deep RL. Think of it like giving the AI a set of rules or constraints up front, rather than making it learn everything from scratch. This neurosymbolic approach can significantly improve sample efficiency and, more importantly, allows for better generalization to new environments. For developers, this means potentially faster training times, less reliance on massive datasets, and RL agents that are more robust and adaptable. It's a step toward making RL more practical for real-world applications where data is scarce or expensive. Also making waves today is research focused on making large language models more accessible. A paper titled Accurate Table Question Answering with Accessible LLMs explores the task of answering questions based on data in tables, but with a twist. Instead of relying on gigantic, proprietary LLMs that cost a fortune to use, the researchers are focusing on smaller, open-source models. This is a big deal for leveling the playing field. It means smaller companies and research labs can participate in LLM-powered applications without breaking the bank. For software engineers, it means more options for building TQA systems, less vendor lock-in, and the opportunity to fine-tune and customize open-source LLMs to specific needs. Next up, a clever approach to text clustering. A new paper introduces twist: training-free and label-free short text clustering through iterative vector updating with LLMs. The key here is that it requires no data preparation and no labeled examples. It's particularly useful for short texts like user utterances and chatbots, where labeling data is time-consuming and expensive. The method uses an LLM to iteratively refine vector representations of the text, gradually grouping similar texts together. For AI practitioners, this offers a quick and easy way to automatically organize unstructured text data without the need for extensive data preparation or model training. This could be a real game changer for streamlining chatbot development and other text analysis tasks. Finally, we have Magma, a multi-graph-based agentic memory architecture for AI agents. This paper addresses the limitations of how LLMs handle long-term memory. Current memory systems often treat everything as one big blob, making it difficult to retrieve specific information and understand relationships between events. Magma proposes a more structured approach, using multiple graphs to represent different aspects of memory, like temporal relationships, causal connections, and entity information. This allows the agent to retrieve more relevant information and reason more effectively. For developers, this could lead to AI agents that are more intelligent, more reliable, and better at understanding and responding to complex situations. It's a crucial step towards building AI systems with genuine long-term reasoning capabilities. And one more. There's a paper on video LLMs addressing the problem of accurately captioning moments in untrimmed videos, called TA prompting, enhancing video LLMs for dense video captioning via temporal anchors. They found existing models struggle to pinpoint the exact start and end times of events. Their TA prompting method is all about better defining those boundaries, leading to much more accurate and grounded captions. For AI practitioners building video analysis tools, this means potentially far more reliable video search, automated video editing, and more detailed summaries. This advancement could unlock a wide range of applications, from security systems to content creation. That's the news for today. Now let's dive into our deep dive topic, the ethics of AI-driven personalized medicine and the potential for bias in algorithms that predict patient outcomes. I was scrolling through Archive this morning and saw a paper claiming a 98% reduction in energy consumption for time series forecasting. And, my first thought was, okay, here we go again. Spiking neural networks. It feels like we get one of these every year, promising a revolution that never quite materializes.
I know exactly the feeling. It's the fusion power of AI hardware. It's always 10 years away. But this SpikySpace paper, I think it's actually different. It feels like two separate threads of research that were running in parallel finally just clicked together.
Okay, I'm listening. What's the click? Because usually the story is, we used SNNs, so it's efficient, but the accuracy is terrible, or it only works on MNIST. The abstract here claims competitive accuracy. That's the part that made me pause.
Right, that's the hook. The key insight is that they didn't just try to bolt SNN principles onto an existing architecture. They picked a fundamentally different backbone. They didn't start with a transformer, which is what most recent attempts have done. They started with a state space model, or SSM.
Ah, okay, so we're in Mamba territory now. That makes sense from a performance perspective. Transformers have that quadratic attention bottleneck, which is a killer. SSMs get that down to linear time, which is already a huge win for sequences.
Exactly, and that's the first half of the puzzle. If you're a developer building, say, a predictive maintenance system for industrial IoT sensors, you're dealing with massive streams of data. You can't afford O(n)² complexity. So moving to an SSM architecture like Mamba, or in this case a new one, is already a good design choice for efficiency. It means you can process longer histories without your compute costs exploding.
Okay, so they're using a more efficient sequence model. That's a good start. But where do the spikes and the 98% energy savings come from? Because a standard SSM is still doing a ton of dense matrix multiplications on every single time step. It's more efficient than a transformer, but it's not that efficient.
This is where the second thread comes in, and it's brilliant. In a standard SSM, you have this hidden state that gets updated at every step. It's a continuous process. What SpikySpace does is make that update process event-driven. The state doesn't update on a clock cycle, it updates when it receives a spike.
So, let me see if I get this. The model is processing a time series, let's say vibration data from a motor. In a normal model, every single data point, every millisecond triggers a full set of calculations. But in SpikySpace, most of the network is silent most of the time. A calculation only happens when a neuron's internal voltage crosses a threshold and it fires a spike.
You nailed it. And this is a perfect match for the selective scan mechanism in modern SSMs. The scan is the core operation that propagates information through the sequence. In SpikySpace, they only perform that scan operation for the neurons that actually spiked. If 99% of your neurons are silent at a given time step, you're doing 99% less work.
Okay, that's the aha moment. They're not just replacing multiplications with additions like classic SNNs, they're fundamentally changing the control flow of the model. The data, or in this case the spikes, drives the computation. This is temporal sparsity, right?
Precisely. It's exploiting the fact that in many real-world time series, not much is happening most of the time. The motor vibration is stable, the traffic flow is normal. The interesting stuff is the anomalies, the changes. Spikes naturally occur around those changes, so you're focusing your compute budget on the parts of the signal that actually contain new information.
All right, let's bring this down to the middle. As a developer, this sounds great in a paper, but how do I actually run this? This isn't something I can just pip install and run on a T4 GPU in Colab, is it? The whole premise relies on hardware that can natively handle these event-driven computations.
You've hit on the most critical point for anyone trying to implement this. No, you can't. This entire architecture is designed to be run on neuromorphic hardware. Think Intel's Loihi chips, SNNs, brain chips, Akida. These are physical processors that are designed to be idle until a spike arrives. They don't have a constant clock cycle driving computation everywhere.
So if I'm an engineer at a company making, say, smart wearables for health monitoring, my workflow is completely different. I'm not writing PyTorch and exporting to Onyx. What does my dev loop look like?
Your dev loop changes dramatically. First, you'd likely be using a specialized framework like Lava, which is Intel's software stack for Loihi, or SNNs, which adds spiking dynamics to PyTorch for simulation. You design your network in that framework, but training itself is tricky. You can't use standard backpropagation because the spiking function, the firing of a neuron, isn't differentiable.
Right, it's a hard threshold, an all-or-nothing event. How do they get around that?
They use something called surrogate gradients. During the forward pass, you use the non-differentiable spiking function, but during the backward pass for calculating the gradients, you substitute it with a smooth, continuous approximation, a surrogate. It's a clever trick that lets you use gradient descent to train a network of non-differentiable neurons.
So I've trained my model using surrogate gradients in a framework like Lava. Now what? I can't just put that in a Docker container and deploy it to Kubernetes.
Nope, the next step in your CI/CD pipeline isn't Docker build, it's a compilation step. You take your trained network and use the Neuromorphic hardware vendor's SDK to compile it down to a hardware configuration. This process maps your Python-defined neurons and synapses to the physical neurosynaptic cores on the chip. It generates a binary that you then flash onto the device.
That sounds fragile and very vendor-specific. Debugging must be a nightmare. You don't get a stack trace, you get a chip that's either producing the right spike patterns or it isn't.
It's a completely different paradigm of debugging. You're looking at spike rasters, checking neuron firing rates and trying to figure out if a part of your network has gone silent or is chattering too much. It's much closer to hardware debugging than traditional software debugging. This is why the paper's other contribution is so important.
The part about simplifying the activation functions? I saw that. They replaced SILU and SoftClus. Why does that matter so much?
Because on a standard CPU or GPU, calculating an exponential for a function like soft plus is trivial. It's a single hardware instruction. On a neuromorphic chip, complex transcendental functions are incredibly expensive. They often have to be emulated with lookup tables or iterative algorithms, which completely destroys the energy efficiency you were trying to achieve.
So any gains you got from this spiking architecture would be immediately lost the moment you hit a complex activation function.
Exactly. By creating simplified, hardware-friendly approximations of these functions using only additions, subtractions, and bit shifts, operations that are super cheap on digital logic, they ensured the entire model end-to-end can be efficiently mapped to the neuromorphic hardware. It's a full-stack optimization, from the high-level architecture down to the individual arithmetic operations.
Okay, so let's talk about the results. They claim a 98.73% energy reduction compared to iTransformer. That's a massive number. But what's the trade-off in accuracy? Is it a 50% drop?
That's the kicker. It's not. They show it's competitive. In some of the standard time series datasets they tested, like electricity and weather, it performs on par with or sometimes slightly better than the baseline SNN models, and it's within a few percentage points of the big, power-hungry transformer models. You're taking a tiny acceptable hit on accuracy in exchange for a nearly 100x reduction in power.
So for an application like on-device keyword spotting on a smart speaker or fall detection in a medical device, that trade-off is a no-brainer. Battery life is everything. A 2% drop in accuracy for a year of battery life instead of a week is a deal you take every single time.
Absolutely. And think about the scale. An industrial site might have thousands of sensors. A city might have 10,000 traffic cameras. You can't have a GPU attached to each one. This technology enables intelligence in places where it was previously impossible due to power or thermal constraints. You can now run a sophisticated forecasting model on a device powered by a coin cell battery or a small solar panel.
Okay, so let's put this into a practical context for our listeners. Who should be dropping everything to read this paper, and who can just file it away as interesting future tech?
I'd break it down like this. If you are a platform engineer or an MLOps person building internal platforms for data scientists using standard cloud GPUs on Kubernetes, this is fascinating, but it won't change your kubectl apply commands tomorrow. Your world is still PyTorch, TensorFlow, and Triton Inference Server.
But if you're an embedded systems engineer, a firmware developer, or an ML engineer working on anything for the far edge, robotics, autonomous drones, industrial IoT, automotive, you need to be all over this.
Yes, if your job involves looking at datasheets for MCUs and FPGAs and worrying about your power budget in milliwatts, this paper is a blueprint for your next-generation architecture. You should be downloading frameworks like Lava or SynTorch today and starting to experiment. Get a dev kit for one of these neuromorphic chips and see what it takes to get a simple model running.
And what about the data pipeline? I imagine you can't just feed a CSV file into this thing. The data needs to be converted into spikes first.
That's a key implementation detail. It's called spike encoding. You have to decide on a strategy. Are you using rate encoding, where a higher analog value translates to a higher firing rate, or latency encoding, where a higher value means a spike fires earlier? This pre-processing step becomes a critical part of your model's design and can have a huge impact on performance. Your data_loader.py script just got a lot more complicated.
So the engineering challenge shifts. It's less about wrangling YAML files for distributed training and more about the physics of the problem. How to best represent continuous real-world signals as discrete asynchronous events.
Exactly. It's a return to first principles in a way. The paper even provides benchmarks on memory traffic, which is another huge cost on edge devices. Because the activations are sparse, mostly zeros, you're not constantly reading and writing huge, dense tensors to and from memory. That also contributes massively to the energy savings.
So when I look at a project on GitHub, I should be looking for things like surrogate gradient implementations or custom activation functions if I want to see if they're serious about neuromorphic deployment. It's a different set of patterns to look for.
Right. If you see a model architecture that uses standard ReLU or GELU and is being called neuromorphic ready, be skeptical. The authors of SpikySpace did the hard, unglamorous work of rethinking every single component to be hardware aware.
Huh. So it really is a bridge. It's not just a lab experiment. They took the best ideas from the large-scale sequence modeling world, the SSMs, and meticulously re-engineered them for a completely different compute paradigm. It's not just make it spiky, it's rethink it for spikes.
That's the takeaway. This isn't just another SNN paper. It's a systems-level design paper. It's about how to co-design your model, your software stack, and your hardware target to achieve something that's impossible if you only focus on one layer of the stack. For a certain class of always-on, low-power applications, this isn't just an incremental improvement, it's an enabling technology.
That's AI Daily for today. If you found this valuable, take a second to subscribe wherever you get your podcasts. And if you're on YouTube, hit that like button. It really helps us reach more people in the AI community. For deeper dives and weekly roundups, sign up for our newsletter at aidaily.sh. Share this with a colleague who needs to keep up. See you tomorrow.